Good morning, students. Welcome to my YouTube channel, Understanding Concepts. Our today's topic is Successive Approximation Type Analog to Digital Converter. I have also explained the other types of analog to digital and digital to analog converters in my previous lectures. You can check the links given in the description box. So let's start with the today's topic, that is a successive approximation type analog to digital converter. As you can observe from the block diagram, here we are having four paths in the circuit, and here you can see it's a SAR, that is a successive approximation register. In the previous discussed counter type analog to digital converter, we were here having the n bit counter. That is the major difference between both of the analog to digital converters. In that counter type analog to digital converter that was being explained by me in my previous lecture, we were having a limitation, a disadvantage of the circuit was that it was having a delay in the process. Basically it was a very slow processed counter, that is a converter, counter type analog to digital converter, and it was taking to convert the analog form to the digital 2 raised to power n minus 1 clock pulses, and that particular problem is being solved here in the successive type approximation register by replacing the n bit counter with the SAR, that is a successive approximation register. All the other parts of the block diagram are the same as in the previous one. So this is a SAR that will provide the digital output, and when we will going to start the circuit, the SAR will provide always the MSB as 1, all the other bits are 0. So we can here have a up to n bits digital output. We can have according to our requirement 3 bit digital output, 4 bit digital output, and up to n. So whatever the number of bits will be here, when we will start the circuit, the MSB will be 1. And this is a DAC, that is a digital to analog converter. The output of the SAR will be provided to the DAC, and that will be generating the corresponding analog voltage. After this, we are here having an operational amplifier that is being behaving as a comparator. It will have this VD, that is the corresponding analog output from the DAC, and we will also provide it the VIN, that is the analog voltage to be converted from the analog to digital form. So it will compare both of the inputs and give the corresponding output. And then here's a logic circuit that will provide the clock pulse to the SAR. According to that clock pulse or the signal, the SAR will change its outputs. So first of all, suppose we are here considering a 3-bit digital output of the SAR. We will consider all the cases, possible cases for the inputs. So we are having two conditions. When this is a 3-bit, when we will start the SAR, then after the circuit is on, the MSB is 1, the all other bits will be 0. When we will be going to start the circuit, the first output from the SAR will be 100. We are taking the 3-bit output, that's why we are taking the first bit as MSB is 1, all other bits are 0. Then this is being provided to the DAC, that is a digital to analog converter, and this DAC will generate a corresponding analog voltage. Suppose 100. For this digital the digital input, the corresponding output voltage is 4 volt. Fine. So now this and this input will be provided, and this comparator will compare both of the inputs. Now we are having two conditions, like VIN, that is this analog voltage being provided, is greater than VD. If this voltage is greater than VD, then what this SAR will do is it will change the output according to this condition that set your next bit. As like this bit is already set, it will set the next bit if Vn is greater than Vd. So suppose we are here considering the different cases, like suppose first of all we are having 1 0 0 output at the SAR, that is the successive approximation resistor. Now we are having two conditions, like in the first condition V in, that is the input voltage is greater than Vd, then set your next bit, it will set the next bit. We will be having this bit already set, it will set the next bit, it will be also 0 1 and it will be 0 1 1 0. And if suppose in other case Vn is less than Vd, suppose Vin is less than Vd, then the output of SAR will be like set bit is going to be reset. It is already set bit, it will reset the set bit, 1 will be converted into 0, and will set the next bit, it is 0, it will convert it into the 1 and again 0. That means according to the two conditions there will be algorithm. If Vn is greater than Vd, it will set the next bit, the bit that is already set, it will remain set, and the next bit will be set, and this 0 will be as it is 0. In the other case, when Vn is less than Vd, then what it will be converted like 1 that is already set will be reset, the next bit will be set, that is from 0 to it will be 1, again 0. Again for the both of the cases we will be having two cases, Vn is greater than Vd, Vn is less than Vd. So here if Vn is greater than Vd, then if Vn is greater than Vd, set your next bit. Now this second bit is already set in the previous you can say in the previous manner. So here we will be having 1 1 1, right? Now if Vn is less than Vd, it will reset the set bit like 1. In the previous round we have set this bit, it will reset it and it will set the next bit, like it will be 1. And in this case it we will be having again the two conditions, Vin is greater than Vd, that means it will set your next bit 0 1 and next bit is from set, that means from 0 it will be converted into 1. Again here we are having Vn is less than Vd, then set bit is going to reset, this bit is set, it is going to reset 0 0 and will set the next bit, that means 1. Again we will be having two cases, if Vn is greater than Vd, then set your next bit. Here we are not having the next bit to set, so it will be remain as it is. Again Vn is less than Vd, then it will set bit will going to reset, this bit was being set in the previously, so we will be having 1 1 0, it will be reset and will set the next. We are not having any next bit, so it will be 1 1 0. And in this case 1 0 1, Vn is greater than Vd, then it will set the next bit. We are not having any next bit, so it will be this. So Vn is less than Vd, it will reset the set bit 1 0 and will set the next bit. We are not having any next bit, so it will be 1 0 0, it's 1. So it's 0 1 1. In the first case, if Vn is greater than Vd, it will set the next bit. We are not having the next bit, it will be 0 1 1. In this case, if Vn is less than Vd, it will reset the previously set bit, it will be this, and set the next bit. We are not having next bit, so it will be 0 1 0. And in this last case we will be having two conditions. V in is greater than Vd, it will set the next bit. We are not having next bit, so 0 0 1. And V in is less than Vd, that means it will reset the set bit. It's 0 0 0 and will set the next bit. We are not having next bit, so it will be 0 0 0. So this is the algorithm we have created. Now we will see how the given input voltage is being converted into the digital in lesser clock pulses. Now we will consider an example. Suppose we have given here a 1 volt to be converted from the analog to digital form. Now we will check. First of all, when we will start the circuit, here we will be getting 100 like this, in this case 100. Now this will be given here, 4 volt will be given here, because this will convert 100 to the 4 volt. This will be given here. We are here providing a 1 volt. It will compare. Now you can see Vn is less than Vd, so it will go to the this second case. Vin is less than Vt, that means directly the SAR will give the output like 0 1 0. Now here we are having 0 1 0 0 1 0, because Vin provided by S is less than Vd. We are here now this 0 1 0 DAC will convert this digital output into the analog. This is 0 1 0, so the corresponding voltage will be 2 volt. Now again this comparator will compare. Again in the case it's 1 volt and it's 2 volt. Again Vin is less, so it will jump. Vin is less than Vd, it will jump here, that is 0 0 1. Fine. Again that means it will now give us the the output 0 0 1. Again digital to analog converter will convert this 0 0 1 into the corresponding output, that is 1 volt. Now here we are having 1 volt. Now this 1 volt and this 1 volt will be go here and comparator will compare. Now you can see we are not having any condition like when the V in is equal to Vd, so the this circuit will stuck over here 0 0 1 0 0 1, it will stuck over here. Then we can here having the output, that is 0 0 1. That means this 1 volt is being converted, this one analog form is converted into 0 0 1, and that is equal to 1 basically, according to the 8421 code. You can have another examples also according to the algorithm. We can have we are here are considering a 3-bit circuit. You can here consider the 4-bit output also. Basically the thing is we have converted the analog to the digital output in basically 2 clock pulses. Maximum to maximum this 3-bit circuit will take 1 2 and 3 clock pulses. In the previously explained analog to digital counter, that was a counter type, it was taking 2 raised to power n minus 1 clock pulses, and compared to that this one is a very much fast converter that is taking only 3 bits the 3 clock pulses to convert the analog input to the digital. So this is the faster one. So you can like compare both of the circuits. You can check the counter type analog to digital converter explained in my previous lecture. You can check the link given in the description box. Thank you.